In this video, we will see another set of signal generators, known as the multivibrators. Multivibrators are electronic circuits that are used to generate non-sinusoidal signals like square wave, triangular and pulse waveform. There are three types of multivibrators, namely, bistable, astable and monostable multivibrators. A bistable multivibrator is a circuit with two stable states. The output can remain at any of these two states indefinitely until it is forced to change by some external sources. A bistable multivibrator built using an op-amp looks like this. Note that the amplifier is in positive feedback. Now, when the circuit is powered on, assume that due to the noise present in the circuit, the voltage V+ at the non-inverting terminal is slightly greater than ground potential. In this case, as the amplifier is in positive feedback, the output saturates to plus Vsat as VID is positive. The output will remain at Vsat indefinitely and hence, this is one of the stable states of the circuit. Now consider that when the circuit is powered on, the voltage V+ at the non-inverting terminal is slightly less than the ground potential due to noise. In this case, the output saturates to minus Vsat as VID is negative. Again, the output will remain at minus Vsat indefinitely and hence this is the other stable state. The circuit cannot remain V+ equal to 0 for long, as any disturbance due to noise will force the output to either plus or minus Vsat. The voltage at the non-inverting terminal is beta times V out, where beta is R1 by R1 plus R2. The state of this bistable circuit can be changed by applying an external input at the inverting terminal. This is none other than the good old Schmidt trigger that we have already seen. The output changes state if Vn rises above beta Vsat or drops below minus beta Vsat. The bistable multivibrator has the characteristics of a flip-flop, which is widely used in digital electronics. The bistable multivibrator is also used to reverse the power supply in some circuits. The next type of multivibrator is an astable multivibrator. An astable multivibrator is the one which has no stable states. The output keeps changing between the two quasi-stable states continuously. If you consider the bistable multivibrator, the output changes state only if external input is provided. So, if we somehow derive this input from the output itself, then the bistable multivibrator will be converted into an astable multivibrator. This can be easily done by using an RC branch. When the output is at plus Vsat, the capacitor starts charging through or towards Vsat. Once the voltage across the capacitor reaches beta Vsat and exceeds a bit, VID becomes negative and hence output switches to minus Vsat. Now once this happens, the capacitor starts discharging exponentially towards minus Vsat. Once it reaches minus beta Vsat and exceeds a bit, VID becomes positive and the output switches back to Vsat. This goes on indefinitely. Thus, the circuit has no stable states, but goes on toggling between the two quasi-stable states, namely plus Vsat and minus Vsat. Thus we have built a square wave generator. Recall that using a comparator, we converted a sine wave into a square wave. But this circuit generates the square wave on its own without taking any input. The time period of the circuit can be found out by adding the charging and the discharging times of the capacitor. The charging equation of the capacitor is this. Note that the initial voltage of the capacitor is VLT, that is, minus beta Vsat. The voltage across it at time t1 is VUT, that is, beta Vsat. Substituting and simplifying we get t1 equal to Rc into ln 1 plus beta, upon 1 minus beta. Similarly, the discharging equation is this. The initial voltage across the capacitor in this case is VUT, that is beta Vsat, and the final voltage at time t2 is VLT, that is minus beta Vsat. Substituting and simplifying we get t2 equal to Rc ln 1 plus beta, upon 1 minus beta. Hence, The total time period T is T1 plus T2, that is, 2RC ln 1 plus beta upon 1 minus beta. Substituting beta as R2 upon R1 plus R2, and setting R2 equal to 1.164 times R1, we get T equal to 2RC. Hence, the circuit generates a square wave at a frequency 1 by 2RC. The square wave generator can be converted into a triangular wave generator simply by integrating the square wave output. We have already seen how to build an integrator using an op-amp. So, connecting that to the output of the Astable multivibrator gives us a triangular wave output. We get a triangular wave of the same frequency by setting our 3C1 equal to T. The third type of multivibrators is the Monostable Multivibrator. This multivibrator has only one stable state and the other is a quasi-stable state. It can remain in the stable state indefinitely and can be triggered into the quasi-stable state, in which it stays for some time before coming back to the stable state. So, in our Astable multivibrator, if we somehow make one of the two quasi-stable states as stable, it would be converted into a monostable multivibrator. This can be easily done by connecting a diode across the capacitor. By doing this, when the output is plus Vsat, the diode is forward biased, and the voltage across the capacitor remains at VD1, that is, the diode cut-in voltage. Hence, VID is positive and hence this state becomes stable. Now, if we apply a negative trigger input sufficient to make VID negative, then the output changes to minus Vsat. After this, the diode is reverse biased and hence, the capacitor starts discharging towards minus Vsat. Once it crosses minus beta Vsat, VID becomes positive. The output changes to Vsat and the circuit is restored to the stable state. Therefore, we get a pulse of a certain width as the output. The width of this pulse can be found out by again writing the discharging equation of the capacitor. Note that the initial voltage across the capacitor is VD1 and the final voltage at time t is minus beta Vsat. Substituting and simplifying, we get the time period as this. As VD1 is a very small value compared to Vsat, it can be neglected, and hence, we get T equal to RC, ln 1 upon 1 minus beta. We want the input trigger to be as short as possible. Hence, an RC differentiator used to get a sharp trigger. Further, we want only the negative trigger edge. Hence, a diode is added in the path to extract only the sharp negative trigger. Hence, we have built a pulse generator. That's all for this video. If you have any questions, please ask in the comments section below. Don't forget to like, share and subscribe.